let's get started. So first of all, welcome back. Okay, so last time we started to talk about ANN search, okay? And we talked about a very popular paradigm nowadays. So that is proximity graphs. Okay. And in particular, we talked about a method under this category, and that method is called disk ANN. Okay. So now, what do you know about this method? So you know how to construct a proximity graph using the method. So you already know the algorithm. And furthermore, you also know how to answer a query, right? Because this is proximity graph. Come on. The query algorithm is super easy, right? Greedy, right? Okay. So what do you not know at this moment? Okay, what do you still need to know? Analysis. Okay, so that is always the interesting part, right? So why does this technique work? What is the mathematical structure underneath, right? So what can we learn about those mathematical structures? And how can we utilize those mathematical properties to design new data structures, new algorithms? Okay, so now today we're going to start to dive deeper. Okay. We are not ready to analyze this algorithm yet. Okay, so before we can fully understand why this algorithm works, something is sitting between, in between, this algorithm and also us. So in order to illustrate this point, let me just mention something that I plan to talk about next week. Okay, so let's recall that if you want to define this ANN search, you need a metric space, right? So this metric space is defined as a pair. So first of all, that's M, that's a set, right? It can be infinite set, let's not forget that. Also, you have a distance metric, right? So this is something that satisfies triangle inequality, right? Very important. So I can tell you, actually last time I already told you, if you have, say, an input set, okay, of size n, right? This is the input set to your ANN search problem, right? One very, very tough competitor for this problem is sequential scan, brute force scan, right? When I give you a query point, you simply calculate the distance between the query point and every single data point in the set P, and then you are done, right? The only thing is, if you do that, and then the query time is going to be big O of n, because at least you have to calculate n distances, right? So it doesn't sound like a very clever solution. What if I tell you in the metric space, in general, okay, if you don't make any further assumptions, this is already the best thing you can do? That would probably be surprising, right? This is not something I'm going to talk about today. As I said, let's take one step at a time, right? We have a small bite every week, and this is something I plan to talk about next week. Okay. So what does that mean? So it means nobody can promise you a data structure with the following property. Okay, so if, let's say, I dare to say I have, a way to construct a data structure in any metric space, this is MD, that's well defined, right? A one set and also distance metric, with those properties. So as long as you give me such a pair, if I say I can always construct a data structure such that in the worst case, I can answer a query by evaluating less than n distances. Once again, if I dare to make that claim, I must be lying. Okay. So next week, I'm going to give you, a lower bound argument showing that this is impossible. So as you can see, we have already hit a wall, right? Sounds like a dead end, because in the presence of such a strong lower bound, what can you do? So pessimistic, right? Sequential scan is already the best we can do, period, right? So clearly, that's not something we are observing in practice. So as I said, proximity graphs today constitute a paradigm that has been adopted by the industry. Industry people, they really care about efficiency, right? Because this means money. So this means there must be something out there, very, very pertinent to the data sets that are actually observed in practice. And those data sets cannot exhibit very, very bad behavior in terms of this metric space. Because I told you, right? So when the metric space is really, really bad, there's nothing you can do but evaluating end distances, okay? So once again, the implication from this is that if we look at the data out there, there must be something. We don't know what that is yet, but there must be something that explains the wonderful performance of, in general, any ANN method that has been proven to work, including proximity graphs. So I can tell you this question today is still an open question. In fact, proximity graphs, they are not the only paradigm that has been adopted by industry. There are some other methods actually designed by some of you here, have also been adopted by industry. In general, the question is there. Okay, on the one hand, I've already told you, in the worst case, there's nothing you can do. However, on practical data, we can see that a lot of methods are efficient. So then there can be only one explanation, right? There's something about the data. And it's that thing that makes it possible to design methods that are better than sequential scan. Okay. So from a theoretical perspective, we want to prove things. We want to prove that a method is provably fast. Okay. So this is something I would say more rigorous than the industry, right? Because the industry says, okay, as long as something's fast on my data, all good. However, in theory, we have to go to the next level. We have to say, you know what? As long as this certain property holds, then I can prove to you that this method is always efficient, even in the worst case. So this is the thing that is standing between us and the analysis of disk ANN. In general, any analysis of any ANN search method. Okay. Now you can feel we need a way to quantify intuitively how difficult or how easy a metric space really is. Okay. And when the metric space is really, really difficult, we surrender. Defined later. If this quantity is small, by the way, that means intuitively that the metric space has additional properties that make it easy. Okay, if this quantity, which I will define later, if this quantity is small, and then yes, it is possible to do a lot better than sequential scans. So today I'm going to introduce one way, actually I would say the most important way to quantify the difficulty of a metric space in theory. Okay, so this is called the doubling dimension. Okay, so before I continue, let me just remind you about Euclidean data. Okay, say two-dimensional data set, three-dimensional data set, et cetera, right? Clearly, there's a dimensionality there. And if you are able to solve things in three-dimensional space, you must be able to use the very same algorithm to deal with two-dimensional data, right? Because I can always append one more coordinate to you, right? So the implication of this is, the higher dimensionality, the problem at least cannot get any easier, right? It could probably get harder, but it cannot be easier. So in that sense, this dimensionality intuitively, Euclidean dimensionality intuitively captures how hard, this problem is in general, right? So two-dimensional space is probably easier than three-dimensional space, which in turn is easier than higher dimensional spaces. But if you think about the metric space in general, right? I told you it doesn't have to be Euclidean data. It could be, but it doesn't have to. It could be, for example, edit distance, shortest path distance, okay, image similarity, okay, I don't know, you name it, right? But these data, they are not Euclidean. You see what I'm saying? They are not points, right? So all you have is just a distance metric. You don't even get to see the data, because all you can do basically, for example, take two images, and then some oracle is going to tell you, okay, so here is the distance between those two images. Okay. Now, would there be a notion that sounds similar to this Euclidean dimensionality? And this dimensionality, if this notion, which of course I will quantify, right? As you can see, the doubling dimension, right? If we are able to use this doubling dimension or this notion to somehow capture the hardness of the metric space, and then we see one possible way to argue that methods like proximity graphs, they are probably provably efficient on certain type of data in practice. Okay. Indeed, this is the path we're going to take. Actually, this is the path that the theory community has taken in order to attempt to explain the phenomena. Okay. But as I said in the beginning, this question is still an open question. Okay, as you can see, theory always lags behind practice, because in practice, people, through plenty of empirical evaluations, have come to some very interesting findings. And then theory, people get interested, and they try to catch up by trying to explain those phenomena. Okay, so as you will see, the theory that I'm going to introduce has been successful in explaining part of the phenomena. This phenomenon that proximity graphs are very efficient and some ANN methods are very efficient in practice. But this method also has its own limitations. It does not really explain all the phenomena that we can see in practice. Okay. So let me continue with doubling dimension, right? So first of all, I have to define what is a ball, okay? So now remember, this is not a Euclidean ball. Euclidean ball, I need no definition here, right? However, it's very similar to this ball notion. You are familiar with Euclidean points. So here, this P is an arbitrary point from the metric space. Okay, so remember, it may not be a Euclidean point. It could be a string. It could be an image. It could be a document, etc., etc. I don't even have to know what it is. And this R is a real value. Okay, so this is something that's larger, let's say larger than 0. Okay, so this ball, okay, larger than or equal to 0. Okay, let's allow distance 0. So this ball says, okay, I'm going to look at every single point in the metric space, and I try to evaluate the distance between P and Q, and I want to know if this distance is less than or equal to R. If so, and then it's included into this set, and this set is the ball. You see what I'm saying? So the ball has no shape. Okay, it's good to compare it to a ball in two-dimensional space, but you have to remember this is a set, and this set is called a ball. If I were, I could call it a computer, I could call it an apple, I could call it any name by any name. I just happen to call it a ball so that you can draw, connections between what's here and what you are familiar with in Euclidean spaces. So that's the ball. As you can see, this is a set, right? And this could be an infinite set, by the way. Could be an infinite set, right? Okay. Now, so the doubling dimension says this, okay? So what is the smallest value, lambda? Okay, smallest lambda that you can find to satisfy the following property. Okay, the property says you take any ball. Okay, so take any ball of radius r. Okay, any ball. How many balls could you have? Possibly infinite. All right, because this metric space, this M, could have an infinite size, right? You take any ball, okay, and you ask yourself whether the following would happen. So any ball, so this ball can be covered by at most 2 to the power of lambda balls of radius r by 2. Okay, r by 2. Okay, so let's try to make sure we understand all the concepts here, right? So you see, I talk about balls of radius r by 2. I only specify the radius. I have not specified the center of the ball. As you can see, the center is this P here, right? So feel free to take whatever points in the metric space to serve as the centers, right? So all I constrain is, the balls that you choose can have radius r by 2. Okay, if you want something less than r by 2, feel free to enlarge it. Well, that can only increase the set, right? And also, every ball of radius r by 2, that's a set. You see what I'm saying? That's a set. So you take so many balls, and then basically you are taking a lot of sets, okay? And you can union them. You see what I'm saying? Union them, right? And then, by the way, this input ball, this radius r ball itself, that's a set. You know what I'm saying, right? So what the sentence is saying by this cover, right? So this cover here essentially says that the input set, which is this radius r ball, is a subset of this union of the sets you have chosen, and every set being a ball of radius r by 2. Okay. All right. Well, if I do not constrain the number of balls that you can choose, you can say, okay, you know what? Just the size of M, right? Because you put a ball centering at every single point, the metric space M, right? And this will always do, right? But that would be too trivial, okay? And what I'm saying is, how many balls what's the smallest number of balls that you can use to cover this input ball, right? And remember, the radius would have to be reduced by half, okay? And that number, if you take the log, is the doubling dimension. Okay. Well, this is probably too mathematical, right? So that's why I prepared some examples for you. Okay, so these should be very powerful examples to illustrate the concept. Okay, let's consider some special metric spaces. Okay, now let's go to this metric space in one-dimensional space. As you can see, M now is just the real domain. You see what I'm saying? Okay, M, right? M. So here, basically, I'm saying you look at one-dimensional space. Now, what is L2? L2 is the straight line distance. You see what I mean? Straight line distance, but it's one-dimensional, right? So basically, you get X, you get Y. The distance metric is simple, just the absolute difference between X and Y. Okay, good. All right, so that's a metric space, right? Everybody is convinced that this is indeed a metric space. Okay, good. Now let's understand what a ball is, right? What a ball is under this metric space, right? So here, what is the point? Point is just a point, right? But it's a one-dimensional point. You see what I'm saying? Okay, good. Now, what is this R? R is just real value, right? No problem. Okay, so that's easy. Now, what is a ball? That's an interval. Okay, you see, that's a one-dimensional space. It's not a circle, right? It's nothing to do with circle. It's a one-dimensional space, right? So if you say this is P and this is R, and then essentially this is an interval of length 2R. And this interval centers at this point. Okay, all right. So basically, if you look at a radius r interval, so that's just an interval with length 2r in general, right? So here is an interesting brain teaser, right? Look, if I say, look at a ball of radius r by 2, by the way, so that's essentially, r by 2, right? So that's essentially an interval of length r. You see what I'm saying? Okay. So how many intervals of length r do you need in order to cover this interval, which has the length of 2r? Okay. The answer is, I'm sorry, I think I heard it. The answer is 2. Okay. All right. Look. So all I have to do is I will use one interval to cover this part. And then I'll use another interval to cover this part. Okay. You don't need 3 intervals. Okay. 1 is clearly not sufficient. Okay. So if you look at the mathematical sentence, I hope this time it gets better, right? You can see I give you any ball. Now this is just I give you any ball of radius r. So this is just an interval of length 2r. And I ask the question, can you always cover this interval using 2 balls of radius r by 2? And I told you before, a ball of radius r by 2 is simply an interval of length r. Okay, so now essentially the question is, I give you an interval of length 2r. Can you always cover it with 2 intervals of length r? And the answer is clearly yes. So in this case, we can set lambda to be 1 because it's log base 2 of that, right? And this is indeed the doubling dimension of this metric space. Okay. So as you can see, this is one-dimensional space, and the doubling dimension is 1. They happen to be the same, right? Now let's see if this is still the case in 2-dimensional space. Okay, now let's elevate ourselves to 2-dimensional space, and this time we look at 2-dimensional space here, and this L2. Okay, so this time, again, the distance metric says you give me 2 points, and then I measure the straight line distance between them, right? So this time, what is a ball? Now this is really a ball you are familiar with. Okay, so here is a ball. Okay, and this is P. Now this is radius r. Now this is going to be a tough question. Okay, I don't expect any of you to be able to prove it here. You might have heard of it before, but it's very difficult to prove. Now you see, this is a circle, a ball. By the way, what's the difference between a circle and a ball? Circle, only the boundary. Okay, the ball also inside, all right? Okay, so now you got a ball of radius r. And how many balls of radius r by 2 do you need in order to cover this ball? Okay, all right. I don't know if you have heard about this before, okay, but I can tell you the answer is 7. You need 7 balls. Okay, so in order to give you an idea how to place these 7 balls, let me show you the idea. Okay, so basically 1 ball like this, now another ball. All right, you got 6 balls. All right, so if you try to cover everything with just 6 balls, and then you won't be able to make it, or there's something in the middle that you cannot cover. Okay, it's difficult to prove. All right, it's not my intention to prove it here, but if you add 1 more ball, you are going to make it. Okay, so as you can see, this covering property really says something about the distance metric. This is very important because in general, when we deal with metric spaces, we often, we don't really have the details of the objects, and we can only rely on the distances. So we need a notion that's related to distance metrics, distances. And if you think about it, right, eventually everything will have to get down to sets, right? Because we don't really have coordinates to reason with. Now, when it comes to set, and then very naturally, in retrospect, that this coverage property is one way to characterize how difficult this metric space really is. Okay, so the answer is 7. And therefore, what is the doubling dimension of this two-dimensional space? You solve this equation, and then interesting, it's a fractional number. It doesn't have to be integer. I never said this doubling dimension has to be an integer. Okay, so it's actually log base 2 of 7. Okay. All right, now I hope this is going to give everybody some idea about this doubling space, right? So in general, I can tell you, if you talk about d-dimensional space, let's say you still talk about L2 norm, okay? And then there is a relationship between the Euclidean dimensionality and the doubling dimensionality. And the relationship is this, okay? So D is the Euclidean dimensionality, and lambda is the doubling dimension. Lambda is at least D. However, not too much larger. There is a universal constant here, C, for some universal constant. This universal means this constant does not really depend on what D is, how large D is, okay? So there's always a constant factor blow up at most, okay? So this doubling dimension, you can say that's at the order of D, okay? Now, importantly, this is something I will not explain in the seminar, but something for you to think about, okay? Now, remember, we're talking about generic metric spaces, right? And they don't have to be Euclidean distances, right? So think about this so-called tree metric, okay? So let's say I give you an arbitrary tree. It doesn't have to be binary, doesn't have to be balanced, it can be any strange tree you can give me, okay? I can also define a metric space. Look, this time, this M includes all the nodes in the tree, okay? All the nodes in the tree. So this time it's a finite, okay? All the nodes in the tree. And what is the distance metric? The distance metric says this, look, you pick any 2 nodes in the tree, and then you calculate the shortest path distance in the tree, okay? Shortest path distance. And then there are many variants here, because depends on how you put weights on the edges, right? So let's just say that every edge has a unit weight. And then this is basically saying how many edges there are on the path, the shortest path, okay? Shortest path from one point to the other, right? So now that's a distance function. Well, this is actually a metric, something that you can prove, okay? It satisfies triangle inequality. Now, here is something for you. What is the doubling dimension of this guy? Okay, so now I have a metric space, M and D, right? So think about it. So it's bounded by a constant. You figure out what that constant is. But just so you know, this doubling dimension is not something that's useful only to Euclidean data. It's useful in general. Okay, good. All right. All right, so now we understand this doubling dimension, and let's use it, okay? So this doubling dimension has a lot of interesting properties that we can utilize. And today I will prove only one. Actually, in the lecture notes, I have 2, but I guess let's start with one first, right? Because I have only 1 hour. And if we cannot finish the other one, actually the other one is for several seminars down the road, it's not going to be useful today, okay? However, it's something nice. So that's aspect ratio lemma. Today, I will talk about the first one, the covering lemma, okay? Now, this covering lemma says the following, okay? So you think about any ball. So let's talk about this lemma, okay? So once again, this is called covering, the covering lemma, okay? You think about any ball that's defined, right? Your freedom to choose what is P, your freedom to choose what is R. Okay, so that's a ball, any ball, I don't care. Now, I can always cover it by how many balls? Now, look at this, K times lambda. And what is the lambda? I just defined, right? Lambda is the doubling dimension of the underlying metric space. Now, what is K? K is any integer, and I will formally define it later. balls, so many balls of radius, okay, r over 2 to the power of k, okay, for any k larger than or equal to 0. So k is an integer. Integer. I'll prove it only for integer. Integer. Okay. This is actually an easy lemma, okay, but I guess if this is the first time you get exposed to doubling dimension, it might take you a while to figure out why. Okay. All right. So let's first understand it. Look, if k is 0, and then basically it says if k is 0, if k is 0, let me see. If k is 0, then basically says it's trivial, right? Because BPR can be covered by one ball of radius r, right? Okay, just itself, right? Okay, good. So if k is 1, and then it says BPR can be covered by 2 to the power of lambda balls of half the radius, right? So this will be r over 2 here, right? Hey, that's just the doubling dimension, right? So it's guaranteed, right? Okay. Now you can see why it's easy, right? Induction. Okay, good. Some of you are getting it. So this is just extending, basically, the property promised by the doubling dimension, right? So let's prove it quickly. Well, clearly, induction, right? So let's prove the base case. The base case is k being 0, and that's trivial. I told you, right? So let's say in inductive case, let's say correct for k being I. We want to argue that this is correct also for I plus 1, right? Okay. Now correct for k being I, so that tells us that PPR covered. Now cover, don't think about covering the shape, all right? There's nothing about shapes here. It's about sets. PPR is just a set, right? So the set's covered, so it's a subset of some union. So PPR is covered by 2 to the power of I times the lambda balls of radius r over 2 to the I. Okay, all right, so that's from the induction, right? Inductive assumption. And then it's easy, right? Now every ball, now by doubling dimension, right? And actually doubling dimension is lambda, we know that, right? So every ball, that's a subset, right? That's a set, right? So every ball of radius r over 2I, okay? So that's a, r prime. Think about it as r prime, okay? Now, as promised by the doubling dimension, right? So every ball is covered by at most 2 to the power of lambda balls of half the radius, r prime by 2, right? And r prime by 2 is r over 2 to the power of I plus 1. Okay, good. Now you connect the dots, right? So here, as you can see, the original set is covered by 2 to the power of I times lambda. But every of this ball, each of these balls can be covered by another 2 to the power of lambda, right? So this is just like, expanding this ball of radius r to the power of 2 to the I with 2 to the power of lambda balls whose radius is to the power of, over to the power of I plus 1, right? So it's like one ball replaced by 2 to the power of lambda. So in general, how many balls you have in the end? 2 to the power of I plus 1 times the lambda of radius r over 2 to the power of I plus 1, all right? So, and therefore, Q ED. Okay, so as I said, this is a simple lemma, and this is something that we get from this doubling dimension, right? So I think at this point, everybody here can feel why the doubling dimension is helping us. If I do not have this notion, you don't really have any of such kind of properties, okay? But because we have successfully introduced the right notion. And then here you have all these properties. Okay, but it's very important when we do research, right? It's very important to keep an open mind. Someone has proposed this notion, good for them, congratulations, but don't take it for granted that this is the only notion that could ever be defined. As I said, this question is still out there, right? I give you a metric space. In fact, I would go even more specific. Look at, for example, the data sets that Huawei is interested in. Okay, and would you be able to identify something that characterizes those data sets? Okay, there should be, because otherwise this ANN search problem will be too hard. And we should not be able to see that some method always works on that kind of data. There must be something there. So the doubling space, the doubling dimension gives one potential way, and this is actually a success story from the theory community. However, I'm sure if you say that this captures all the cases, it will be extremely controversial, right? So I want to remind you that the question is still there. However, think about the methodology. I think the methodology is making a lot of sense. You need to introduce some properties, and then you can prove things under those properties. Good. Now, disk ANN. I hope you still remember the algorithm. Okay. So basically, the algorithm computes this proximity graph by processing every single point in turn, right? And the processing for every point is symmetric. So let's just talk about one point, okay? So my goal is to prove that for any point, this disk ANN is going to generate only a small number. Okay, okay, so that's going to be a bound. Before, I was not able to prove any bound other than n minus 1, okay? But now I will be able to prove another bound, which could be small when this doubling dimension is small, okay? So here is my goal. So my goal is to prove that, this is basically 1 over epsilon to the power of lambda. And then, there's something, this delta. I will talk about this delta here later, but you can ignore it, okay? But what is really important is the other terms. 1 over epsilon. What is epsilon? You want 1 plus epsilon ANN. Don't forget, right? This is something tunable. Now this lambda, so that's the doubling dimension, okay? And this bound holds when the doubling dimension is a constant, okay? Otherwise, you will have another term like 2 to the power of lambda out there, okay? So, or some constant out of lambda out there. So it's exponential to the doubling dimension, okay? I'll explain this log delta term later, okay? Later, that's not the point here. But as I was saying, right? So this does not really explain all the success of proximity graphs. However, if the doubling dimension is small, let's say it's two-dimensional space, two-dimensional. Still remember what is the doubling dimension of two-dimensional space? That's less than 3. Okay, that's a 10-dimensional space. All right, so 10-dimensional space, the doubling dimension is going to be larger, but still it's at the order of 10. So what's the takeaway measure? Well, you have to remember n is huge, like 1 billion or 10 billion, et cetera, et cetera. If the doubling dimension is small, and then you expect to see that the number of out edges or the out degree of a point is significantly less than n. And that explains why you don't really need all the edges. Last time I told you, right? So in the worst case, you need a complete graph. But in practice, maybe if the data is easy, you don't need a complete graph. Okay. So let's prove this, all right? Now, we are still 2 lemmas away from proving this. Okay, so let's start with the first one. But I feel the need to help you recap the algorithm, right? So let's quickly recap this disk ANN algorithm. Let's say this algorithm says get out edges. And we take a parameter P. Okay, so P is a point in the data set. Okay, so let's see how we generate the edges. Okay. All right, so first of all, sort everything else. Sort, let's say L. Okay, sort everything else. So big P is the input set, small p is the point that we're working on. So you sort everything else in ascending order of distances to p, small p, okay? Sort everything else. And then you want to process the sorted list one by one. Okay, and if this sorted list is empty, you are done. Okay, but if L is not empty, you do the following. Okay, so first of all, you get the next point. Next point on L. Okay. Now you want to create an edge. Create an outgoing edge for P. Okay, so that's PU. As you can see, this is ordered here, right? So from P to U. Okay, good. So one outgoing edge. But then, you know, the clever part of this ANN is that it will kick out a lot of points, all right? A lot of points that are close to U. You see what I'm saying? Still remember the picture that I gave to you? Okay, so here's the picture. Okay, so P, let's say you got somebody V's, and P is Singapore and V is Boston, right? So this is an example I gave last time, right? I don't know, I found it very intuitive. P is Singapore and V is Boston, right? So let's say U is New York. You see what I mean? U is New York, right? So let's say we have already got a direct flight from P to U, right? And intuitively, you know, we're not going to build another direct flight from Singapore to Boston, right? So that doesn't make sense, right? But we need a map way to do this formally, right? So if we say, well, this distance is less than 1 over alpha of the distance between P and V, and then we don't do it. Okay, so from P to V, so that's huge, right? So that's you know, transcontinental, right? So that's very far, so very far. Now, if let's say alpha is 10, right? So if the distance between New York and Boston is less than 1/10 of the distance from Singapore to Boston, and then no direct flight is necessary. Okay, so basically this is what this algorithm does: kick out every V such that this is true. So distance of UV is less than 1 over alpha times the distance of P to V. Okay, good. All right, so that's the algorithm. Okay, now let's do some analysis. Okay, let's do some analysis, right? Now, this P is the main player. Okay, that's why it's in red. Now, remember, every discussion, you know, all our subsequent discussion revolves around this P. Okay, so you think about this donut. You know, donut. Let me give you a donut. Okay, donut. All right, so let's see what the donut is mathematically. Okay, so think about this S. S is the donut, by the way. Think about this PR. So that's a ball, right? That's a ball, right? Now I want to set minus, set difference, right? So from this set, I want to kick out something. Now what do I kick out? I kick out another ball, but this ball has radius r/2. And that's a donut. Do you see why it's donut? So you see why it's a donut, right? Good for you, right? You see, geometrically speaking, that's the ball, correct? Okay, so that's radius r. Now let's say this is r/2, right? So what I want is everything in here, okay? And I do not want the boundary of the inner ball, right? So the boundary of the inner ball is excluded, okay? So that's the donut, right? Good. All right, so here is what I want to prove. Now, so that's the algorithm. I'll leave it there. Now think about 2 points. Okay, so P1, P2 within the donut. P1, P2, they are not P, by the way. Okay. And P1, P2, they are close to each other. They're just like Boston and New York, right? So the distance between P1 and P2 is less than or equal to R over alpha. So 2 times alpha. Okay. So 2 times alpha. So this is 2, this is alpha, right? So my handwriting this alpha looks like 2, all right? So 2 times alpha. Okay, so you can see if alpha is 10, then this is essentially saying very small, right? Or by 20. Okay, so they're very close. If this is the case, the lemma says, then only one of them, at most, one of P1, P2 can be an out neighbor of P. Okay, so basically it says Boston and New York, if they satisfy this condition, either Boston or New York can be an out neighbor of Singapore. Not necessarily New York, but if it was not New York, then it has to be Boston, and then New York would not be an out neighbor. Okay, only one of them at most. Okay, only one of them. It's not possible that both of them will become out neighbors. Okay, so let's prove it. All right, so this is not entirely trivial, so we have to look at the algorithm. Okay, now think about the argument. So 2 points, P1, P2, without loss of generality. Suppose P1 positions earlier in the list. Let's say ranks earlier than P2 on L. Now, what is L? Now, remember, L is saying, I'm standing here, I'm Singapore, I'm sorting out all the other points in ascending order of their distances, right? So basically saying P1 cannot have a farther distance than P2, right? Because it stands before P2 on the list, at most it could be a tie. You see what I'm saying? Okay. All right, good. So let's think about the behavior of the algorithm. Okay, so first of all, if P1, so the better guy, is not of P, all right, the better guy, let's say New York. If New York is not an out neighbor of Singapore, we're done. Because our goal is to prove, at most one of them can be my out neighbor, right? So now New York is out of the picture, and you told me New York is out, so thank you very much, and I'm done. Okay, all right, good. So if that's the case, it remains to consider the case where P1 or New York is an out neighbor. Now let's consider otherwise. Good. Now, if you think about it, the algorithm's right here, right? So you consider there's only one place where an out edge for P can be created, right? It has to be at line 4. You see what I'm saying? Okay, there's no other place where this out edge is created, right? So this means, at some point, this New York P1 in my proof must be sitting at the position of U. You see what I'm saying? Or in other words, at some point when I scan down the list, I can see that New York or P1 is the next guy on my list when I start a new iteration. Good. Now let's consider that iteration. Okay, let's consider that iteration and see what happens. I'm going to argue that P2 will definitely disappear after this iteration if it had not disappeared before. Okay, so if that's the case, as you can see, number 5, right? It kicks out P2, and then P2 disappears from the list forever, and we say goodbye, and we'll never see that point again, right? So there's no chance that P2 could reappear and become an out neighbor of P, right? So that's the strategy. Good. Now, with everything I have said, I think it should be pretty standard now, right? So the remainder of the reasoning should be fairly straightforward, but I will present it just for the sake of completeness. Okay. So, of course, we have to utilize 2 conditions, right? So first of all, this P1 and P2, they are very close to each other. That's one. But don't forget, we also need the property of the donut. Okay, the donut here, right? So let's see why both properties are needed. Okay. Well, first of all, let's think. Let's think about the distance between P and P1. So P is Singapore and P1 is New York, right? So let me remind you about donut, right? So P1 will have to be in here. You see what I'm saying? And it cannot be on the boundary of the inner circle. Okay, so we can say that the distance is strictly larger than R/2. You see what I mean? Strictly larger, right? Why? Because P is the center of this donut, and the inner circle has radius R/2, right? And P1 is in the donut. Okay, so S, right? So you can see P1 and P2, there are 2 points in S. So on the one hand, I have this inequality. On the other hand, you told me that these 2 points are fairly close, right? So because you told me that P1 and P2 is less than or equal to this, right? So now I can claim that this P1, P2 is less than or equal to D times P, sorry, the distance between P and P1 over alpha, okay, by utilizing these inequalities, okay? So now I have this inequality, and because of this inequality, I know that P2 must be eliminated, okay, in this iteration, provided that it has not been eliminated earlier. Okay. So this is basically the essence behind this strategy utilized by this RNN, this ANN. As you can see, it makes sense, right? So now here you will not be doing a lot of unnecessary, let's say, out edges. Good. All right, so now let's look at the next lemma, and this will bring us very close to the proof. Okay, so let's do it here. All right, the second lemma, we already have this lemma 1. Okay, so let's say this is lemma 1. Now let's look at lemma 2. Now still consider this donut. Same donut as before. Okay, so same donut. Okay. Now I'm going to argue that at most, how many points? At most 4 times alpha to the power of lambda points in the donut can be our neighbors. Okay, so this is the second lemma. Okay, at most so many points in S can be our neighbors of P. All right. Okay. All right, so before I prove this, let's take another look at this covering lemma that we proved earlier. Okay, so this covering lemma is the gem provided by this doubling dimension property. Okay. Now, in order to make sense of this lemma better, I want you to look at this 2 to the power of k as some sort of radius, some sort of distance. Okay, so let's call that t. Okay, and now this denominator is basically t. You see what I'm saying? You can think about t as some power of 2. Okay, so now this is saying if you've got a power of 2, and then I can say this power of 2 over, sorry, this power of 2 to the power of lambda. So that's the number of balls, but then the radius will be r over this power of 2. You see what I'm saying? That's the relationship. Okay, good. Well, let's look at this lemma here. And so for simplicity, let's assume that alpha is a power of 2. This is just to make my job easier. Okay, I'm not going to prove the case where alpha is not a power of 2. I have the whole proof in my lecture notes, but this is really, really tedious. Okay, so once you understand what's going on here, you just adapt the proof. All right. So I don't want to be bothered with stealing. So that's all. Okay. So let's say alpha is a power of 2. Okay. So I'm gonna reason as follows. Okay. So I want to look at this t being 4 alpha. You see what I'm saying? Still remember I said think about the gem given to us by doubling dimension, right? So it says t to the power of lambda, that's the number of balls. And then in turn, the radius will be r over t, right? Okay, good. Now this t is a power of 2, isn't it? Right? So alpha is a power of 2 and 4 is a power of 2. So t is a power of 2. So by the covering lemma, we know that, this BPR, so don't forget the look of the donut, right? So this BPR is the larger ball, okay? Inside the ball, that's R over 2, okay? So this PBR is covered by T to the power of lambda balls of radius R over T. All right, so this is the jam. This is the covering lemma, right? Okay, good. So think about this as a set, by the way, as a set, okay? So as you can see, let me see, 2 times alpha, where is it? Here. So this this B is a set. So that's a ball, right? So this set contains this donut. You see what I mean? This donut is also a set. Everything here are sets, okay? So you have this set containing a smaller set, which is the donut. So even the big set is covered by all these balls, let alone the donut. You see what I'm saying? And therefore, this says, so is the donut S. Okay, good. All right, now let's look at every ball. Now you can see the ball has radius R over T, right? So R over T, so let's expand it. So this is R over 4 times alpha. Okay, R over 4 times alpha. Now let's look at this ball. All right, so let's say P1 and P2, they are inside here. So my question for you is, do you think that both P1 and P2 can be our neighbors of P simultaneously? No, okay, good. I like you to shake your heads now. Okay, so that's encouraging. Why? Because we just proved this. Okay, by lemma 1, we have proved that if P1 and P2 their distances at most this, only one of them, at most one of them, can be an out neighbor of P, right? But do we have this? Well, this is the reason why I chose this radius to be something over 4 times alpha, right? Because if these two guys are inside this little ball, and then their longest distance can be only double the radius, right? So doubling the radius gives you R over 2 times alpha. Okay, good. So because of this, only one of them, let's say, only one of them, okay, basically you look at all the points inside this ball, at most one of them can be the winner, can be the lucky guy, right? So this is an out neighbor of P. So now I've got so many balls covering the donut. Okay, so donut is here, I cover it with a lot of balls. And I've proved to you that in each ball, I can have at most one lucky guy. Okay, by the way, it does not necessarily mean that every ball has a lucky guy. So this is an upper bound, right? So this donut is here. I cover it with lots of balls. And in every ball has only one lucky guy that could be an out neighbor of P. So the number of lucky guys, out neighbors of P, cannot be more than the number of balls. You see what I'm saying? And therefore, this bound that we have, where's that bound? Where is that bound? It's covered by T to the power of lambda, right? So T, as you can see, is equal to 4 alpha, and this is exactly what we're claiming here. Okay, good. Now, this is the second lemma, okay? I will need another 5 minutes today, okay? So now what have I proved? I have proved that feel free to choose whatever donut you want. Okay, so basically here, this donut, where's your freedom? I mean, what's your freedom? You don't really have the freedom for P. You see what I'm saying? The P is our main player here. But you do have the freedom to choose the radius. You see what I'm saying? You can choose the radius whatever way you want. So now the question is, how can you choose the radius so that you can prove that, overall, this P cannot have too many our neighbors. All right, so this is the last part. Actually, in the lecture notes, I left it as a corollary, which means this is something good for you, right? So this is very nutritious question for you to think about. Okay, but I will outline the idea here, right? Still remember I had this delta, right? So this delta is something mysterious. Okay, something mysterious. So what is delta? Well, this is the aspect ratio of the input P. Now, what is the aspect ratio, right? Aspect ratio, if I talk about a rectangle, everybody understands what aspect ratio is. But I'm not talking about rectangle here, right? So you got this P. All right, so let's say D min. This is the smallest interpoint distance. Okay, this is someone would say this is the distance of 2 points in P. Well, almost correct, except that these 2 points could be the same, in which case their distance will be 0. Okay. All right, so this is the smallest interpoint. Smallest interpoint distance in P. Interpoint. So these 2 points got to be different. You see what I'm saying? And what is smallest distance you can have for 2 different points in P? Okay. Now for D max, and then this is the largest interpoint distance in P. Okay, so this is essentially the diameter, by the way, of the data set. Diameter. Okay, so what's the largest point distance? Right. Now this delta is defined as D max over D min. Okay, D max over D min. So this is the aspect ratio. Okay, aspect ratio. Now let me show you how to choose this value of R, this donut, right? But without loss of generality, let's say this D min is 1. So this D max is delta. I can always do this because I can scale. I mean, it's just a function, right? So I can scale it down, let's say by D min, and then I get this D min to be 1, right? So let's say this is true. Now what I want you to do is this. Look, I want you to first choose this donut to be the following, right? So I want you to choose, say, let me see. So I want you to choose R to be 2 to the power of 0. Okay. So now I have, so let me see how to choose this. Let me see how to choose this. Okay, so let's say I start from 2 to the power of 0, and then I choose R to the first one is R to the power of 0. Okay. So now the donut will cover, if you think about it, right? So this R will be saying from 1 over 2, as you can see, it's open on the left-hand side, okay, to R to the power of 0. All right, so this is R to the power of 0, and 1 over 2 is R over 2, right? So this is saying, if you look at P, right? So if you look at this particular distance, so think about a lot of concentric circles around P, right? So you see, I'm talking about this area here. Okay, and by the way, there can be nothing inside the green circle because inside the green circle is at most 1/2 to P, right? The distance, right? But I've already told you that the minimum distance between 2 different points is 1, right? So from in the black area, you start to have, points, right? All right, so now the next thing I want to do is from 0 to the power of 1. So essentially, I want to build a bigger circle here. Okay, basically starting from the place where I left off in the previous cut. You see what I'm saying? So now this time, the donut will be between the second circle and the third circle. You see what I'm saying? Okay, so now this is the second donut. Okay, now if you union the black and the green region, sorry, the black and the red region, and then you can see that so far we have not missed any. Okay, all right, so this is the second region, right? So in terms of radius, as you can see, I'm basically partitioning the whole possible range into two intervals now, but I need more intervals. So I'll do it here, right? So now this is 2 to the 2 to 2 to the 1 to the 2, right? So now you can see I create another donut outside. Okay, so now here's, I think you have already got the main idea, right? So you create logarithmic number of such kind of concentric circles, and then you can convince yourself all the data points eventually will be covered by at least one donut. But the thing is, within every donut, we proved earlier, right? You can have at most 4 alpha to the power of lambda. How many donuts can you have? Well, you can prove for yourself. You only have a logarithmic number of donuts, and it's a logarithmic to delta. Okay, so this proves that the number of edges is at most this number times log delta. Okay, all right. So that's everything for today. Okay, I'll see you next week. Bye-bye.